So let's start by talking about how to count things in groups. So, whenever you get eggs from the grocery store, they're not sold as individual eggs, they're sold as a group of 12. So, 1 dozen is always equal to 12 things. So, it could be 12 eggs, 12 cars, 12 people, whatever. A dozen is always 12. So that's a convenient number to count eggs by because a dozen eggs is about what you might use in a couple of weeks, something like that. But how would we count atoms? So atoms are very, very small, but we also count them in groups. So rather than using a dozen to count atoms, we instead use a mole. So 1 mole is equal to 6.02 times 10 to the 23 items. And it could be atoms or molecules or eggs or cars or people or whatever, but a mole is always that many. So let's explore this mole relationship a little bit. We're going to compare an elephant and a methane molecule. So an elephant has 1 trunk and 4 legs, kind of like how a methane molecule has 1 carbon and 4 hydrogens. So if I had a dozen elephants, I would need to multiply 12 times 1 trunk per elephant, and that would give me 12 trunks. We could also just say that this is a dozen. Okay, what about legs? So if we have 12 elephants, they each have 4 legs. So when I multiply here, I get 48 legs. Or we could also just call that 4 dozen legs. Okay, so what about in a dozen methane molecules? So each methane molecule has 1 carbon atom. So that means that a dozen of them will have 12 carbon atoms, just like the trunks. And again, we could just call this a dozen. We can do a similar calculation for hydrogen atoms. Each methane molecule has 4 hydrogen atoms. So we have 48 hydrogen atoms total, which we could also just call 4 dozen. Okay. So what if we had a mole of elephants? So a mole isn't 12, a mole is a different number. It's 6.02 times 10 to the 23. So if I multiply that by 1 trunk per elephant, that's going to give me 6.02 times 10 to the 23rd trunks, which we could also just call 1 mole of trunks. Okay, so what about legs? So if we have a mole of elephants, and each of those elephants has 4 legs, this is going to give us what, 24.08 times 10 to the 23rd legs, which we could also just call 4 moles of legs. Now, that would be a lot of elephants. If there were a mole of elephants on the planet, we'd all be, walking on top of elephants. But whenever we use this mole number, we're using it to describe atoms, which are very, very small. So, how many carbon atoms would be in 1 mole of methane molecules? So, 1 mole of methane molecules is 6.02 times 10 to the 23rd molecules, and each of those has 1 carbon atom. So I've got 6.02 times 10 to the 23rd carbon atoms, which we could also just call 1 mole of carbon atoms. For hydrogens, if we have a mole of these molecules and each of them has 4 hydrogen atoms, that means that I'm going to have 24.08 times 10 to the 23rd hydrogen atoms, which we can also just call 4 moles of hydrogen atoms. So how is a mole similar to a dozen? They both allow us to count by groups. So you can count eggs, 1 egg, 2 egg, 3 egg, or you could count them in groups, 1 dozen, 2 dozen, 3 dozen. We can count by atoms, individual atoms like eggs, or we could count by moles of atoms. So a mole is equal to 6.02 times 10 to the 23rd items, which is a very, very large number. Why would we want to use that to count atoms with? So atoms are very small. So you have to have billions of them in one place before you can even see the substance. So we want to count them in large groups because there's a lot of atoms in a sample or in a compound. So now let's look at these mole ratios a little bit more closely. So now that we're familiar with how to count by moles, let's look at different conversion factors I can use with moles. So the first one that we have up here is particles. So particles is just a general term. So particles could mean molecules. It could mean atoms. It could mean ions, etc. We also have volume for gas, so we measure that in liters, and we measure mass in grams. So what this is showing you is that, let's say that I have 10 grams of hydrogen, and I want to know how many molecules that is. I can't go from grams directly to particles. I need to first change grams into moles, and then change moles into particles. So how do we change something from grams to moles? We're going to use molar mass. So to find molar mass, we need to look at the chemical formula and then use the periodic table to look up the molar mass of each element, multiply it by the number of atoms in the compound, and then add it all up. So let's do a couple of practice problems here. So these are written as names, and we want to first determine their formulas, and then we can use the periodic table to find their masses. So sulfur dioxide is a covalent molecular compound, and the formula for this is going to be SO2. So in this molecule, I have 1 sulfur and 2 oxygens. So I'm going to look on the periodic table and find the molar mass for sulfur, and then I'm going to find the molar mass for oxygen. So when I do this math here, I can get my answer. That's just going to be 32.06, and then this is going to be 31.998. And so now we want to add these numbers together, and this gives us right around 64.06 grams per mole. So those units are grams and moles, which means that this number allows us to convert between those units if we have some grams of sulfur dioxide and we want to know how many moles there are. The next one is lead 2 nitrate. So this is an ionic compound. Lead is a metal, and this particular lead has a +2 charge indicated by the Roman numeral. Nitrate is the polyatomic ion NO3, and it has a -1 charge. So I'm going to need 2 of these in order to balance out the +2 on lead. So that 2 is telling you that we have 2 nitrates. So I've got a lead, a nitrate, and another nitrate. So for lead, we only have 1 of those. Nitrogen, we have 2. And oxygen, we have 6. So I'm going to look up the molar masses here and multiply it by the number of atoms. To get my answer here. Okay, so now that we have all of those numbers, we can add them together and we'll get the molar mass for this compound. It's going to be around 331.2, and the units on this are grams per mole. Let's take a look at phosphoric acid. So this is an ic acid, which tells me that this stem here originally ended with 8. So this was originally phosphate. So phosphate is the polyatomic ion PO4, and it has a -3 charge. Since this is an acid, we're going to start with hydrogen here. And hydrogen has a +1 charge. It's in that first column on the periodic table. So in order for these charges to balance out, I'm going to need 3 hydrogens. So we have a total of 3 hydrogens, 1 phosphorus, and 4 oxygens. So I'm going to go ahead and do my math here. Phosphorus has a mass of 37.974. And oxygen is going to be 15.999. And we're going to multiply that by 4. And then we want to add all these numbers together. So when I add those together, I get 97.99 grams per mole for phosphoric acid. The last example here is ammonium sulfate. So ammonium is the polyatomic ion NH4, and it has a +1 charge. Sulfate is SO4, and it has a -2 charge. So in order for these charges to balance out to 0, I'm going to need 2 of these nitrates. So this is telling me that I have a nitrate, a second nitrate, and a sulfate. So we've got nitrogen, hydrogen, sulfur, and oxygen. I've got 2 nitrogens. Hydrogens, we've got a total of 8. Sulfur, there's only 1 of those. That has a mass of 32.06. And we've got a total of 4 oxygens. And that's going to give me this number. So once again, add it all together, and I get that my mass is 132.14 grams per mole. Okay, so now that we're good on using molar mass here, now let's get into doing some actual problems where we're trying to convert between units. So looking at question 12, we're starting with particles of sodium chloride, and we want to change that into grams of sodium chloride. So I'm starting with particles, which is up here, and I want to get down here to grams. So I can't just go from particles directly to grams. I've got to follow the mole roadmap here. So I'm going to change particles into moles using this conversion factor, and then moles into grams using molar mass. So up here at the top, I recommend that you write in a plan. So we're going to change this from particles to moles, and then from moles to grams. So until you get really good at these problems, I recommend that you always set up a plan here. This is going to guide you through the next step. So we have 1.56 times 10 to the 30 particles of NaCl. And we're going to start by just putting that over 1. So that 1 is just a placeholder. We want to change particles into moles. So if you take anything and divide it by itself, it's going to be equal to 1, right? If you do 10 million divided by 10 million, it's equal to 1. If you do x divided by x, it's going to be 1. So if we divide particles by particles, that should cancel out. So I'm going to want to divide by particles to cancel out that unit. So I'm going to put particles of NaCl on bottom. And in this first step, we're trying to change particles into moles. So if we wanted moles, we would be done here, but we want grams. So we're going to use one more conversion factor. So I want to cancel out moles this time, and I want to change it into grams. Okay, so now that we have this set up, particles would cancel particles, moles will cancel moles, and then the only unit left is grams. So now we need to fill in these conversion factors here. So the first one that we have is moles and particles. So how many particles are in a mole? I'm going to use this number here. So 1 mole is going to be 6.02 times 10 to the 23rd particles of NaCl. The next conversion factor is grams and moles. So I'm going to use molar mass in order to do that conversion. So I need to find the molar mass of sodium chloride. So sodium chloride, we've got Na, which has a mass of 22.990. And then we've got chlorine, which has a mass of 35.45. So when I combine these together, I get a molar mass of 58.44 grams per mole. So this is telling me that if I have 1 mole of NaCl, it's going to weigh 58.44 grams. So to solve this, I'm going to multiply everything on top together, multiply everything on bottom together, and then divide. So I'm going to need to do 1.56 times 10 to the 30 times 58.44, and then I'm going to need to divide this by 6.02 times 10 to the 23rd. So remember that for these numbers that are in scientific notation, that you should put parentheses around them. Your calculator doesn't understand order of operations, so if you're not careful in how you type it, you might get the wrong answer. But when I type this all in and solve, I get 1.51 times 10 to the 8 grams of NaCl. Let's look at another one. How many oxygen molecules are in 3.36 liters of oxygen? So I can't go from liters directly to molecules. I need to change liters into moles of oxygen. Then I can change moles into molecules of oxygen. So that's our plan here. So in this problem, we are starting up here with liters, and we want to get over here to molecules. So first I'm going to start with my 3.36 liters of O2 over 1. In this first step, I want to change liters of O2 into moles of O2. And then I want to change moles of O2 into molecules of O2. And that will give me my answer. So my first conversion factor here has moles and liters. So I need to find a number that has units of moles and liters that will allow me to do this conversion. So 1 mole of any gas is 22.4 liters. My next conversion factor is molecules and moles. So remember that particles is a generic term. So 1 mole of O2 is going to be 6.02 times 10 to the 23rd molecules. So whenever we solve this, we're going to do 3.36 times 6.02 times 10 to the 23rd. And then we want to divide by 22.4. So when I do that and solve, my answer is 9.03 times 10 to the 22 molecules. Question 15, we're starting with molecules. We've got 2.00 times 10 to the 23rd molecules of F2. And we want to get to grams. So I'm going to change molecules into moles, and then I can change moles into grams. So 2.00 times 10 to the 23rd molecules F2. We're going to change molecules into moles. And then we can change moles into grams. So 1 mole of anything is going to be 6.02 times 10 to the 23rd molecules. And this other one here is molar mass. So for fluorine, we've got 2 of those. And we're going to multiply that by the mass of fluorine. And this will give us our molar mass. So the molar mass for fluorine, 1 mole, is 37. 0.996. So to solve this one, I would need to do 2.00 times 10 to the 23rd times 37.996, and I need to divide by 6.02 times 10 to the 23rd. So when I do this, the answer that I get is going to be 12.6 grams of fluorine. Number 15, determine the volumes in liters occupied by 14 grams of nitrogen gas. So remember that nitrogen is one of those diatomics. It's going to be N2. Now we want to figure out how many liters this takes up. So we can't go from grams directly to liters. We're going to go from grams of nitrogen to moles of nitrogen and then into liters of nitrogen. So starting with our 14 grams of N2, we want to first change grams of N2 into moles of N2. Then we can convert moles of N2 into liters of N2. So our first conversion factor here is grams and moles. So I need to figure out the molar mass of nitrogen. So that's going to be 2 times the molar mass of nitrogen, which is 14.007. So this is telling me that 1 mole of nitrogen is going to weigh 28.014 grams. Now we need a conversion factor that has liters and moles. So 1 mole of any compound of any gas is 22.4 liters. So to solve this, I need to do 14 times 22.4, and then I need to divide by 28.014. And when I do, I get an answer of 11.2 liters of nitrogen. Okay, question 16. Find the mass in grams of 1.00 times 10 to the 23rd molecules of nitrogen. And we want to know how many grams this would weigh. So I can't go from molecules directly to grams. I always got to go to mole in between. So I'm going to start with my 1.00 times 10 to the 23rd molecules of N2 over 1. I'm going to convert molecules into moles in this first step. And then I can change moles of nitrogen into grams of nitrogen. So my first conversion factor is moles and molecules. So 1 mole is always 6.02 times 10 to the 23rd molecules. The next one that we have is grams and moles, and we already found the molar mass of nitrogen on the previous slide. So I'm just going to fill that number in here. So in order to solve this, I'm going to need to do 1.00 times 10 to the 23rd, multiply that by 28.014, and on the bottom I'm going to divide by 6.02 times 10 to the 23rd. So when I do my math here and I solve this, I get 4.65 grams of nitrogen.